Good evening, everyone. This is Celso Batalha, Evergreen Valley College. This is Astro 10, and um, I hope you had a great Thanksgiving and recharged your batteries. You are ready to complete this semester. We have 3 or 4 weeks to go, and pretty much semester is over. I would like to remind you we have a midterm number 3 open, and it will be closed midnight tonight along with other assignments. Another piece of information I would like to remind you is that we have a makeup midterm, and this makeup exam or midterm is pretty much comprehensive, covers most of the topics related to the student's learning outcome that you can check in your um, syllabus. And it will be used to swap the lowest score you had in previous midterm in case your grade in this makeup exam is bigger, right, than the lowest score you had in previous midterm. In case you get a score that is less, nothing happens, right? So you just keep with your average midterm as you have so far. And then we have our final exam. Don't forget, your final exam is face to face, so you have to be present. I will allow you to bring a page of notes back and forth. You can write as much as you want, but in such a way that you don't squeeze the entire book information in in a minute font size and have a um, magnifying lenses helping you to read through. Okay, so pretty much chapter 14 is a chapter that introduces galaxies. So our course was pretty much organized in the following following matter. 1/3 of it is pretty much solar system. So we focus on what we see in the sky, what type of stars are, excuse me, out there, what's the difference as we see in from the observational point of view, just with a naked eye, what's the difference between stars and planets, and what's their apparent motion, what is causing their apparent motion, not only on an hourly basis but also throughout the year. And then we move on to pretty much gauge what are the main tools astronomers use to uncover the mysteries of the universe, and pretty much is light. All the information, all the knowledge we build about objects out there is pretty much dependent on what we observe through light. When light interacts with matter, matter imprints characteristics of pressure, temperature, velocity, or projected velocity, if you will, into light. And when astronomers collect light and analyze light, they can infer the properties of a gas responsible for interacting or responsible for producing the light we observe. So that was chapter 4, and then we had we traveled through the history of astronomy, also in this first 1/3. Now, then we move on. We learn about the sun. We learn about the solar atmosphere, its 3 main layers, and the solar interior, production of energy in the sun. And then we initiated the study of stellar evolution and HR diagram. That's very important. And then we learned stars are formed out of a cold gas and dust. Gravity contracts them, and eventually a circumstellar disk of cold gas, relatively cold when you compare with the star, is responsible for producing most of the solar system objects we know of, with exception of sun, it's said. But planets, satellites, and asteroids, comets, and zodiacal light, all these different components came out of this remaining gas that circled the star in its initial phase of evolution. And then the star becomes a main sequence, and then eventually the core, the hydrogen core, is depleted of hydrogen. The star undergo further evolution, and depend on if the star is less than 8 solar masses, the star expands out to be a giant star, and then eventually becomes a horizontal branch stars and start pulsation, and then eventually go to asymptotic giant branch and become planetary nebula, white dwarf. That is those main steps in the evolution of a low mass star. But if you think about the high mass stars, it's basically the same, except that the core undergo further nuclear reactions. It doesn't stop in carbon and oxygen, and then the star ends its life with a megatonic explosion, if I can use this term. In fact, it's much more than that, and that's the so-called supernova type 2. And then all heavy elements are formed out of this explosion. But anyway, so and then pretty much this star, right? So now we are studying not a star, but a complex group of stars, hundreds of billions of them together, and we call that a galaxy. So this chapter 14, Measuring Galaxy, in fact, introduce, and I will go browse through the PowerPoints and pretty much introduce what galaxies are. And there are different types of galaxies, and we are going to see them in a second. And they are the so-called spiral galaxies, elliptical galaxies, and the so-called irregular galaxies. And then we are going to outline what are the main difference between those types of galaxies. So do they have specific shape? You can, if you see a picture of one of them, can say, okay, that is a spiral galaxy. By the way, our Milky Way is a spiral galaxy. And spiral, you know what a spiral is, and you will be able to clearly, as you contemplate the picture of a spiral galaxy, identify it as a spiral. And they have different features, different characteristics, and that's what we are pretty much probing. Now, and then we are going to explore different types of velocity motions or star motions in the galaxy itself. When you observe elliptical galaxies and you follow stars in these elliptical galaxies, they seem to have some specific type of motion, which is different from spiral galaxies. So there are some differences in there, and then we are going to be specific of what produce so much activity in the very core, the center part of these galaxies. And then we find there is a supermassive black hole in these cores. So, and as we explore these different types of black holes or supermassive black holes, millions of solar mass in the core of galaxies, we realize that certain galaxies, the black hole is extremely active. And those galaxies are called, by activity, they produce lots of radiation, they produce a firework that by far outshine the activity our galaxy itself has. And those galaxies are called AGN, active galactic nuclei, AGN. And then we are going to finalize this section by observing that in our galaxy, most of the material in it is not the material we observe with telescopes. In fact, most of the material controlling the dynamics of galaxies, we don't know what it is, called dark matter. And that is 90% of what brings gravity in fruition in galaxies. 90% or more is not baryonic matter made of protons, neutrons, and electrons, but is something else. We don't know what it is. It's called dark matter. There are candidates for it: machos, which we'll see what it is, and WIMPs. WIMPs, which we'll see what it is too. And then the last part of this chapter is to say, hey, if you observe galaxies, you find that they are expanding. They are up away from certain millions of light years from us. We see galaxies expanding away. They are moving away. They are receding from us. And the explanation for this receding motion is not exactly the fact that galaxies are themselves moving, but the space in which they are happen to be stretching. And then which was one of the major achievements of astronomy in the 1920s, that the universe is expanding. So there is the space in between galaxies is stretching. And as this stretch go on, the separation between galaxies increase, and so the speed or the projected velocity in which we see them. Okay, so let's browse over the PowerPoints. So one of the principles, and when we studied galaxies and the universe in large scale, and these principles pretty much came up after we observe in detail the universe in different directions and after modeling the universe to match observations. And that is the so-called cosmological principles. So the cosmological principle states that, well, the laws of physics we use here in our local universe, which means the laws of gravity, the laws of gas, the laws of thermodynamics, are the same everywhere. So there is not a specific part of the universe in which the laws of nature happen to be different. I mean, we assume they are the same, and this seems to be a reasonable assumption. At least so far, we didn't find a part of the universe the laws haven't or are different, because we haven't been there yet. Like let's say here, the gravity, if you hold something and let it go, it's going to fall down towards the massive Earth. But if I happen to be standing on a different planet somewhere else and I let something go, it's not going to fall down, but it's going to move up. So as if the laws of gravity were different, matter would repel matter. So we assume that matter will always attract matter, no matter what it is. It might be wrong, but so far we haven't found a counter example. Now, if we assume this is true, there are some predictions that can be made, and that is the universe is homogeneous. So what exactly that means? Well, it means if you take a scoop, imagine you can come up with a gigantic dipper, and then you take a scoop of the universe in a different locale, and then you measure galaxies in there, you measure the density and the distributions of galaxies in this particular locale, and then you find some characteristics of it. And then the homogeneous universe states that if you go to another locale, another place, and you do the same exercise, certainly in a larger scale, in the scale of several hundreds of millions of light years. So if you do the same exercise, you find the distributions of galaxies is basically the same. In a sense, our universe is a string of superclusters of galaxies surrounding voids. And if you analyze these different structures in different locales, you find them exactly matching one another. So that is the principle of universe being homogeneous, like a bowl full of flour. So if you take a scoop of flour in different parts of this bowl, it will be the same. The density it will be the same. The color will be the same. The distribution of granules will be the same. Everything is going to be the same. That's what it means to be homogeneous. This is not true in small scale. Like certainly the distribution of mass in our solar system is not homogeneous. You have more mass in the sun than you have in the planets. the distribution of mass in our Milky Way is not homogeneous. You have a massive black hole in the core, and you have stars that are going around the circumstellar disk. Perhaps the dark matter is homogeneous and goes around the halo. But if you think about stars alone, the distribution is not homogeneous. But if you extend your reach and you include not just our local group of galaxies with a few dozens of members, but if you extend it to superclusters of galaxies with thousands and thousands of galactic members, then the universe is homogeneous. Now, isotropic means no matter which direction you look, the universe looks the same in average, right? So you don't have more concentration of material in one direction than in others. You don't have the universe appearing hotter in one direction than in others. So it seems to be isotropic. No matter where you look, it seems to be the same. And those two cosmological principles are important to in the two remaining, in fact, in the three remaining chapters to explain how the universe exactly is. Types of galaxies. I brought a picture here. Let me see if I can bring that on. Oh, not there. There you go. So I have several pictures of galaxies, and you see they are different, right? So when you look at this galaxy, it seems to be similar to this one, right? Why? It has a kind of a bulge, kind of a central bright area, right? And you have some spiral lanes coming out of some region. Same thing here. Although in the second galaxy that I'm showing, the central region seems to be smaller than the spiral lanes, right? But the galaxy type is the same. So let me introduce you to a spiral galaxy. A spiral galaxy is one that has a central, kind of a homogeneous and kind of a smooth bulge with stars, as we will learn, and out of this bulge comes out spiral lanes, as you can see here and there. This is different. This seems to be something I have some idea what it is, but if I look at this for the first time, I wouldn't know what to say. If somebody tells me, okay, this is a galaxy, I wouldn't know if this is a spiral. It doesn't look like a spiral. This looks like a spiral, right? It has a bulge. The bulge is not spherical, it's more lenticular. It has some spheroidal shape, looks like a football shape. And out of this bulge, then the spiral lanes comes out. So these, I don't know, it has a smooth distribution of brightness from the center out, but it has a lane, a dark lane here, indicating that dust is absorbing, is retrieving light from the region beyond the dust. So, but I can't, just with that information, I can't tell what it is. But look at this. This is another spiral, and another spiral right here. This is another spiral galaxy, another spiral, and spiral, spiral, spiral. So spiral galaxies can be easily identified because of their bulge and because of their spiral arms. Now, another type of galaxy is the so-called elliptical galaxies. Elliptical galaxies. Take a look in there. So elliptical galaxies, when you look here, it shows you a smooth distribution of brightness. So it's kind of a brighter in the center, and this brightness diminishes as you move out to the exterior part. Look at it here, and look at there, and look at there, right? So this elliptical galaxy, is saying here, elliptical galaxies universe are smaller and contain less dust than spiral galaxies. But this looks like a spiral. It's a funny galaxy. I don't know what that is. This is a spiral galaxy. This is not elliptical. This is elliptical galaxy. This I don't know. I can see this dark dust lane. This has a dust lane in there. Spiral galaxies, spiral, and spiral, more spiral, elliptical. So you should, elliptical galaxies will not show you spiral lanes. So the spiral lanes are not there, so they are easy to be ruled out as a spiral. See, those two are elliptical. This is an elliptical galaxy, elliptical, and elliptical too. Okay? All right. What is it? There you go. So look at these pictures. So spiral galaxy, this is a spiral galaxy, this is another spiral galaxy, this is another spiral galaxy, spiral, spiral, spiral. So spiral galaxy, one of the interesting aspects of them, it has this flattened disk, thin disk, right? So some galaxies are observed edge on, like this galaxy over here. Edge on means you are looking through the circumgalactic material, circumgalactic disk, and then you can clearly see how thin this disk is, right? So here's the disk, it's very clean. This galaxy is almost edge on, and is a spiral galaxy because of this dark dust lane. See this dark dust lane that goes across? Indicates the presence of dust, and dust can only be formed once cold gas arises. The condition of cold gas can be met, and then this cold gas will crystallize dust that will efficiently absorb the light in the infrared. And in the optical region, and then not in the infrared, but in the optical region, and then we can see this is a dark lane. So spiral galaxies also have a central region that's called the Bouge, the galactic Bouge. Now, in elliptical galaxies, they have a smooth distribution of light, as I mentioned before. Some elliptical galaxies appears as spherical, perfectly spherical, and some elliptical galaxies are elongated. And to differentiate between those that are spherical, we call them E0, elliptical zero. And from those that are severely flattened, we call them E7. And then we have this number between 1 and 7 that gives the different category in which these galaxies are pretty much stretched. Now, it doesn't mean that galaxies are all that way. I mean, sometimes we see a spherical galaxy. If you look at this elliptical galaxy, this one that I'm showing here, right? This one. So if you look at this elliptical galaxy from your telescope using this perspective, you are going to see it spherical like this, right? Think about an airplane. This is an airplane, right? And if you're looking straight into the airplane, you see something like this. The pilots are here, right? So, the shape, as we see in this classification, E0 to E7 doesn't tell much, right? It doesn't pretty much say much. It just say that, well, that's how they appear. Some of them appear elongated, some others don't. Now, irregular galaxies, they are not of a specific shape. They have irregular shapes, and that's why they bear this name, irregular. Okay. Now, let's talk about the stars in these galaxies. So, in spiral galaxies, okay, let's start with ellipticals, since it starts with ellipticals here. Yeah. So in elliptical galaxies, the stars in the elliptical galaxy go around the nuclear part following any given direction. So if this is the central part of a galaxy, so one star might well go like this. Another star might well go like that, right? So they don't have a command in the way they should go. So stars seem to be going in all possible and willing directions. And that is what this little diagram here indicates. Okay. So this is for elliptical. Now, spirals, they are different. Spiral galaxies are such that stars, they are part of the disk. So here's the disk. This lanes here indicates the disk. The star in the disk, they all have the same direction in which they go. Like a herd of cows, they all move in the same direction because they are being called or pulled by some cowboy or cowgirl. They all go in the same direction. So once the galaxy was formed and flattened as a result of gravitational force and angular momentum, like we study stars, the circumstellar disk around the stars follow the same prescription as why the stars in the circumgalactic disk, they all move globally in the same direction. Now, if you look at the center part of the galaxy called the boge, so if you look at the boge, now the orientation in which the stars go pretty much match and looks like similar to the same prescriptions as we found in elliptical galaxies. So stars in the boge of a elliptical galaxy, oh, I'm sorry, in a spiral galaxy, in the boge of spiral galaxy, they go in any possible direction. They don't follow a orientation, global orientation. So elliptical, spirals, and irregular. So what are the characteristics, not just in velocity distribution of the stars, but in the type of content? So elliptical galaxies, they don't have a lot of gas. In fact, the gas that are found in elliptical galaxies, they tend to be hot. Right? They are hot, and more importantly, they don't have star formation, which makes sense. With a hot gas, a star cannot clump. Gas cannot clump to form stars because the gas pressure in hot gas, the gas pressure is such that it promotes outward type of motion, expansion rather than contraction, which is the requirement for formation of stars. Okay. Now, in the spiral galaxy is different. You do have cold gas, and then the star formation is going on. So when you look at elliptical galaxies, stars are old. In general, they are old population because star formation is gone. So the stars that can be found there, they are pretty much done. They evolve and they are pretty much waiting to die. Rather than in spiral galaxies, star formation still goes on, and then new stars are being formed every year. So we have, let's say, in the statistics of 10 or so stars that are formed in our Milky Way every year, so that you can say that in the spiral arms of our galaxy, you have a young population of stars. And in irregular galaxies, since you have lots of gas and the gas is cold, this is very important, you do have star formation going on. Okay. Now, in general, spiral galaxies like our Milky Way, spiral galaxies, they have similar size. So we can say the disks edge to edge, right? So if you take the edge to edge of a spiral galaxy, we are talking about 100 to 200,000 light years in dimension. So it's pretty much standard, right? Now, the elliptical galaxies is different. Elliptical galaxies can be small elliptical galaxies called dwarf elliptical galaxies, but they can also be giant elliptical galaxies. So they have these two categories and in between. And then we found that nowadays it's understood that elliptical galaxies are the result of mergers, of combination and conglomeration of spiral galaxies, and they just add together as a result of gravitational interaction. So all these cold gas of spiral galaxies are used up to form stars, and eventually you ended up with an elliptical galaxy, um, giant elliptical galaxies, and you can find those in the very central core or central area or central volume of dense clusters of galaxies. So that's so much for the size. And galaxy rotation, this is very important. Now, if you look at spiral arms, let's go back to the picture here. So you look at these spiral arms of a galaxy, and you can see it right here as well. It's like right here. Where is it? There you go. This could be right there. So according to Kepler's law, you would expect the stars that are closer to the galactic bulge, this bright area here in the center, the stars would go around the center of the galaxy with a rotational velocity that is bigger than the rotational velocity of the stars that are further out. This is pretty much Kepler's law, and is pretty much explained by Newton's gravitational law. So stars, again, that are closer to the galactic bulge, they go around the galactic center with a speed that is more than it is the stars that are further out. Okay, the problem is this is not observed. In fact, you see that stars that are further out, they go around the galactic center at a growing speed or the same speed as those that are in more inner part. How's that? So either Newton's law of gravitation is wrong or something else is out there. So the common wisdom so far is to assume that this model, the rotational curve of stars in our galaxy, can be explained if it is assumed that the galaxy is embedded, is surrounded by a material that we don't know what it is. It's called dark matter. And this material has the property of being attracted, which means gravity can be produced by this type of material. So what is the main result is that the distribution of dark matter surrounding the galactic halo, going up to 300,000 light years in dimension, and pretty much surrounding the galaxy itself. So this material in the far edge pull these stars that we observe in the spiral disk and bring them to the rotation we observe. Also, dark matter was proposed in 1930 by Zwicky, an astronomer, when he observed that galaxies in dense clusters of galaxies were moving at very fast rate, and this motion would fling these galaxies away. Since they are gravitationally bound to the cluster, the only explanation he found was that there was some insane material, and he coined that as dark matter. But again, last week or so, it came the publication of an article saying, well, maybe we don't know what exactly the space is. The space might play some tricks on us. But dark matter is an important subject here, and that is the galactic, the rotational curve of stars in our galaxy. Okay, so we would expect the rotational curve to be something like we observe in these three curves, but what we see is the last one. Okay, so the stars further out, they have higher speeds than they would have following Kepler's law of motion. So what type of material we don't know, but we have names for it. So the names are WIMPs. Those are the most agreeable candidates, weakly interactive massive particles. And these particles, they pop in and out, and they are not observable. They can't be observed because they short-lived, but they are massive. So if you have a large distribution of these particles pop in and out, but you can't detect them, but every time one of them pops in, it adds mass to the entire environment. So when you have several of them popping in and out at different times, that mass adds up to be what is required to explain what we observe. Okay, now are they being detected? Well, there is an attempt to in the Large Hadron Collider. Perhaps if the physics is right and the intuition of physicists is correct, we might hear about these candidates being finally detected in the next few years. Okay, so those are the main topics of this chapter, together with the expanding universe. So when you observe galaxies in any direction beyond certain numbers, hundreds of million light years, you observe galaxies no matter which direction you look, you observe them receding away from us. Now, this cannot be explained as these galaxies themselves operating this motion, but if the space is the one stretching. And that is exactly what our PowerPoint or classwork explains. So let's say if you have a rubber band with paper clips A, B, C, D, as you can see in there, and then you separate them on a fixed time, let's say, from this configuration here to this configuration here, it takes 1 second. So let's say that, and imagine the space doubles during this 1 second. So from A to B, you have a distance, let's say 1 inch. Same here, 1 inch, 1 inch, right? And then 1 second later, the distance from A to B is 2 inches. So it was 1, now it's 2. It was 1, now it's 2. It was 1, now it's 2, right? Here it was 1, now it's 2. So let's take just this expansion here. Imagine this is a universe expanding on a time rate of 1 second. Now, when you measure the speed in which you see, if you are galaxy A and you see the distance in which galaxy B expanded, so galaxy B was 1 inch away, right, and went to be 2 inches away. So during that second, it expands 1 inch per second. So per second, sorry, 1 inch per second. This is galaxy B. So let's look at galaxy. Galaxy was 2 inches away, 2 inches away, right? Originally. But then the space stretched, and now galaxy is 4 inches away, right? And went to 4 inches. So in which speed you would observe that expansion? Well, no problem. 4 inches minus 2 inches divided by 1 second. So 2 inches per second. See, galaxy B is receding at 1 inch per second. Galaxy C is receding 2 inches per second. So B is 1 inch per second, and galaxy C is 2 inches per second. You can do the same with galaxy D. Let's say galaxy D was originally at 1, 2, 3 inches away, 3 inches away, and was expanded, galaxy D was expanded to 2, 4, 6 inches away, right? So the total expansion was 6 minus 3, 3 inches. And so, and the speed The speed is what? 3 inches, which the separation that it took per second, right? So 3 inches per second. So you see, the further the galaxy is, the faster you seem to measure its receding expansion. So, but it's not the galaxy, it's the space the galaxy is part of. And that is the so-called expanding universe. Now, expanding universe will be taken again towards in 2 chapters from now when we studied Hubble law. Okay, and we'll do that later. All right. Good night to all of you.